Assalamualaikum. Good afternoon.
Waalaikumsalam.
Afternoon, doctor.
Can you hear me?
Yes, sir. Yes.
Okay. This week, I will continue on the PD controller as we discussed last week, where we already gone through P controller, PI controller, and now is PD controller. So let me remind you again, the P controller is a gain controller using a potentiometer, where we can increase and decrease the gain, and it will affect the overshoot and steady state error. Okay, once you increase, the overshoot will increase and the steady state will improve. But when you lower the gain, the overshoot will decrease and the steady state will not improve, becoming bigger. So when the steady state become bigger, so we propose a PI controller, where PI controller is able to increase the system type, okay, so that the steady state will become 0 from a finite value. Then we go to the PD controller, where PD controller is one of the controller to fasten the transient response, okay, increase the speed of the transient response, and you will see that the peak time and the rise time, sorry, the settling time will be shorter, okay? So much faster compared to the before PD controller, before we apply PD controller. So let's go to the second examples, okay? In example 5, where you are given a open loop transfer functions, which is here is open loop transfer function. Okay, so as usual, it is in the feedback control system. Okay, where you have the R, C. Okay, so this is a negative feedback. Okay, so the location of the plant is in GS, in the forward path. Okay, with a unity feedback. Okay, a unity feedback, and you have to determine the overshoot percentage and the settling time. Okay, first problem is to find the overshoot percentage and settling time, and then design a controller to have a 50% reductions in the overshoot, not operating system, overshoot, and 4-fold improvement in the settling time. So what do you mean by 4-fold? Is 4 times improvement of the settling time, the old one. Okay, so TS new will be 1 multiplied by 4, 1 over 4 multiplied by the old settling time. Okay, so you are given these open loop transfer functions, then you derive the closed loop transfer functions. So you will get 50 over s squared plus 5s plus 50. Okay. Then you compare with the standard second order equations, which is given here. Okay. Omega n squared over s squared plus 2 zeta omega s plus omega n squared, where zeta is the damping ratio. and omega n is the undamped natural frequency. Okay, so you can see that from here, zeta and omega n. Do we need to draw the root locus of the system without controller? Can we find the specification needed? Of course, you can from comparing this one. Okay, omega n, you will get what? What is the value of omega n by comparing this? Square root 50.
7.07, doctor. Square root 50.
7.07.
07.
Thank you, Telpa. Okay, and then from there you can compare this part to zeta omega n. Okay, with pi, so zeta is 0.356, and by inserting the omega n value that you get previously, 7.07. Right? So from there, so you can use straight away the formula of TS, which is 4 divided by zeta omega n. So you will get 1.6 seconds, and then the overshoot is 30.45%. This one you can use a graph or you can use a formula. Okay, what is the formula? Which is this formula? Overshoot minus pi zeta over 1 minus zeta square multiplied by 100. Okay, so there is a formula for it, so you can use it. Okay, to get the answer based on the given closed loop transfer functions. Okay, so this one settled. Okay, so the desired settling time is 0.4 seconds, which is 1/4. Okay, this one 0.4 seconds come from 1/4, fourfold improvement multiplied by 1.6, which is 0.4 seconds. Am I right? And the new overshoots will be 15.23 seconds. Okay, 15.23 seconds based on the new settling time. Okay, based on the new settling time. Right, so the desired closed loop now is become -10 plus minus j 16.69, where you have to plot it. Okay, yeah, okay. So zeta 0.356, which is 69.14 to obtain the zeta line. And the dominant pole here is -2.5 plus j 6.5. So you get 7.07 for the omega n before controller, then zeta 0.356. Right? So from the overshoots is 30.5 and TS 1.6 second. That is before controller design. Then after controller design, the spec is 0.4 seconds. Okay, meaning that is a fourfold improvement. That is the meaning of fourfold improvement. And omega n now become 19.49 radian per second. That's why now the dominant pole has been changed, okay, to -10 and plus j 16.73. Okay, that's why the answer here. Okay, right? Then the -10 plus j 16.73 will be the test point over here. Okay, and then yeah, you will get we locate the existing poles, which is the 0 and -5, the open loop poles, and then you put zeros, okay, for the PD controller anywhere on the real axis. Okay, you can put it here, you can put it here, okay, you can put it here, no problem. Okay, just assumptions, the locations, okay. So let's say we locate it here, okay, at minus z, which is over here, and we name it as the angle as theta 3, and then the zeros is theta 1, and minus 5 is theta 2, okay. Right, so for alpha 1, which is 59.13, okay, so if we look here, we are using the angle criteria, theta 1 plus theta 2 minus theta 3. So theta 1 and theta 2 is the angle due to poles at 0 and minus 5, while theta 3 is the angle due to zeros for the PD controller. And therefore, we get the theta 3 is 47.51. Okay, so theta 3 will be here. Okay, so we are concerned on this x, okay, and this z, right? So x is 15.32, so therefore the z will be minus 10 minus 15.32. So the location here is minus 25.32, okay? And the angle is shown here, how to calculate the angle for theta 1, theta 2, and theta 3 respectively. And then after you calculate the angle, and then you start to calculate the length, because the length is related to the K value at this point, okay? You want to know the gain or the K value at that point. So you use the notation L1 is the length between the test point to the zero open loop. L2 is the length between the test point to the open loop poles minus 5. And then L3 is the length between the test point to the new zeros minus 25.32. Okay. So we calculate L1, calculate L2, and calculate L3 using a Pythagoras theorem. And then at the end of the day, you get the K, which is L1, L2, and L3. L1 is due to the zeros, product of length of poles, and L3 is the product length of zeros. Then the K value is 15, which is over here at the minus 10 plus J, 16.73. So for the ratio, okay, for the KP over KD, where we locate the minus 25.29, so the ratio will become positive 25.29, which is the zeros value, okay? And then we know that K is equal to 50 multiplied by KD. Then KD is 15 that we calculate previously here. KD, this is KD derivatives. Sorry, the KP. This is not KD. KP. Sorry, KP. Please correct your notes. KP is a proportional gain. KP is equal to 15, so therefore KD is equal to 0.3, which is KD is equal to KP divided by 25.29. KD is KP 15 divided by 25.29, okay, which is equal to 0.3. So therefore, KD, okay, this is your KD, okay, this is your ratio, okay, which is KP over KD. And this is the open loop poles S plus 5. So you get the P controller there. This is your P controller. Then we redraw again with the PD controller, the root locus. Okay, so the zeros sorry, the poles at zeros there, that is your -5 poles, open loop poles and zeros. And your -25 is somewhere here. Okay, -25.27. 25.29. Okay, so now the root locus will start from the poles and ended at zeros and infinity. Okay, so start from here, and this is a breakaway point. Then goes down here, goes down here, goes down here, and one will end at zeros, the other one will end at infinity. Okay. Of course, there is two cross-section point. Okay, shown here. Okay, so both are valid for this kind of controller. So when we compare the time response with the PD controller, this is before. Okay, so to get this response, so the closed loop transfer functions is here, closed loop, which is 50 over s squared plus 5s plus 50. 50 s squared plus 5s plus 50. That is your closed loop transfer functions before PD controller. Okay. This one. And then for the closed loop, you have to include the where you can see that the settling time is 1.55 and peak is 1.3. Then after PD controller, you cascade it with the S plus 25.29 with the closed loop transfer function. So you will get a shorter settling time at 0.385 and peak time at 0.138 seconds. Okay. So when you superimpose, so you will become this one will become much faster compared to the previous one. Any question? Ada soalan?
The PD system will only improve the TS.
Will improve the TS, meaning shorter settling time.
Shorter settling only.
Shorter settling time and peak time.
Peak time.
Meaning that the transient will be faster.
All right.
Fast response. Any questions? All right, brothers. Is there any question?
Thank you.
Okay. How is your fasting month? Okay. Alhamdulillah.
Yes, Doctor. Alhamdulillah.
Nah, okay. Zai mujahadah, insyaAllah. Try be patient, insyaAllah. Okay. Muhammad Akmal, are you there? Muhammad Akmal?
Yes, sir. I'm here.
Okay, all right, good. Right, so if there is no question, we go to the PID controller. Okay, so PID controller stands for Proportional, Integrate, and Derivative Controller. Proportional, Integrate, and Derivative Controller. Okay. So the modern PID, we call it the digital PID, is shown here. Okay. So this one is when you go for internship with the company that have a control technique, so you will face this kind of controller. Okay, so usually it apply in the process. Okay, So this is a burner process to generate electricity. Okay. There is a control valve here. Okay. And then there is a transmitter. And there is a controller. Okay. There is a set point. Okay. And this is the variables measured, which is CO and PV, right? And then you can also use Arduino Uno. Okay, this is Arduino Uno. During the internship, you can propose to apply in the PID controller. Okay, so this one is for the spark plug control. Okay, using a PID controller. So you must have a set point. Okay, so you must have the process variables. Okay, and the CO. I forgot this. What is the word? Okay, this is the what do you call that? PV, one of the process control variables. Right. So proportional is stand for the KP, the gain. Integral stands for the KI, the integral, and KD is the derivatives. Meaning that we are trying to apply a PI and PD together, okay, simultaneously in one control system, okay. So that's why you have a P, I, and D in the parallel connections, okay. So to be summed and to control the process, which is over here. So PID controller is used to improve steady state error and transient response independently. Okay, so independently meaning that is combinations. We consolidate the PI and PD together. So PID controller is a combination of PI and PD controller. First, begin design for the transient to fasten the transient response, and then design for the steady state error. Okay, so that's why the transfer functions of PID, since the block is parallel, so we sum each other, Kp plus Ki over S plus Kd S. Okay, so when you simplify this equation, so it becomes Kd in front, the derivative, S square, Kp divided by Kd, the ratio between the gain and derivative, and then the last one is Ki over Kd, the ratio between the integral and derivatives. So it becomes a GPI or GPD, then together it will become S, K, S plus Z1 over S. Okay, this one is for the PI, and this one is for the D, PD. Okay, so this one is simple because you have already origin, post at the origin. You just put Z1 0.1 or 0.01. You remember already. But Z2 is quite difficult because you have to calculate the locations of Z2 in order to decide where the response goes. Okay. So implementation wise for the PID controller shown here, where it consists of 2 zeros and poles at the origin. Okay, so you have a K1, K2 over S, and K3 over S multiplied by GS. Okay, so in these examples, okay, we're going to see the examples of the PID controller. So given the system, design the PID controller so that the system can operate with a peak time that is 2/3 of the uncompensated system. Okay, meaning that the new peak time will be 2/3 multiplied by the old peak time. Okay, that is the meaning of peak time, that is 2/3 of the uncompensated system, and 20% overshoots. So 20% overshoot, you will get the zeta value by using the formula or the graph, standard graph, and 0 steady state error. So that is common using a PI controller. for a step input. Step input meaning one vote step. Okay. And the open loop transfer function is given here. So it is a third order system where you have poles at -3, -6, and -10. Okay. And open loop zeros at -8. Okay. So far, okay? Everybody okay? Okay. So this is a third order system. The order is 3. And how about the type? What type is it? The type of the systems. Sadenan Sakit. What is the type of the system? Tak ada. Azira Ahmad. Azira. Assalamualaikum. What is the type of the system?
Not sure, Doctor. Sorry.
Aduh, ya Allah. Nur Aina Syafiqah. Nur Aina, Assalamualaikum.
Salam.
What is the type of the system, Kak?
Type 0.
Type 0. Okay, sebab kat sini because this is S power of 0. If there is a S power of 1, type 1 lah. If there is a S power of 2, type 2. Boleh? Apa tadi tu? Sure. Right? Okay. Everybody okay?
Yes.
Okay.
Okay.
So we plot. Okay. So we plot using a MATLAB. Okay. Using this computer program. Okay. This is option 1. Option 2. To plot this. Mu'tasim. Muhammad Mu'tasim.
Yes, sir.
How to plot? Using a second option coding.
S equals to TF.
S, EF, S, okay. Hello,
G equals to
E equals to S plus 8 divide S plus 3 multiply S plus 6 multiply S plus 10. Okay. Then R locus G. Okay. So you will get this rule locus plot, right? So how many rule locus plot, rule locus path in this drawing? Alicia Zaidi.
3.
Huh?
3 path.
Path, huh? Confirm? Confirm, eh?
I'll confirm.
Okay. Satu. Then 2. Okay. Can. My next question is Aina Nabila. Aina. How many rule locus path ended at infinity? Aina. Ended at infinity. How many? Dua lah. This one, this one, kan? And this one ended at zeros. Betul? Yosef?
Yes, doctor.
What is the name of this point?
It's between two zeros. Break-in
Break
between two zeros and
in or stop over? Break away.
breakaway. Sorry.
Ah, huh? Break away, eh?
Sorry, sir.
Ring, mashallah. So 20% overshoot deals a damping ratio 0.56. You can get into 3 methods. Okay, one is by formula. This one. Second is by formula zeta. Third one is by graph. This one. Okay. So 20% is about here. It goes down here. Okay. So it is 0.456. Okay. So you use a protector from the origin over here, the origin. Okay. So 0.456 is theta 62.87. How do we get 62.87? Ni Umar, how do we get theta 62.87?
Arc cosine of damping ratio.
0.456. Okay. So the dominant pole now is the point where the true locus intersection with the zeta 0.456. Okay. 0.456. So what is the value of the dominant pole from the plot?
Minus 5.42 plus 10.6 I.
Haikal. Muhammad Haikal. What is the value of dominant poles? Tak ada. Haikal nak attend absent Mo Wei Jun.
Yes, doctor.
What is the dominant pole? Intersections between damping ratio and the rule locus line.
-6.
-6 plus no idea. We asked the Royal Raja Ahmad Zahid. Raja,
Yes, sir.
what is the value of the dominant pole? It's written there. This point. No wonder lah, you push more down. Push mark all down, all a blur.
Negative 5.42 plus 10.6.
Aina.
Negative 5.42 plus J 10.6.
Oh, where are you? You from another planet? It's all like yeah, it's a minus 5.42 plus J 10.6. Okay, so that is the dominant pole, and the third pole value. Hello. The class. I'm sorry. Can you call back? I have class. Online class. Okay, the third pole is minus 8.16. How do I get this? Manually. Low Jotian.
Which one, doctor?
Third pole, minus 8. How do I get it?
From the graph.
No, manual. How do you get it? It's by using characteristic equation. Okay.
Okay.
Right. Right. So the desired closed loop pulse is here in the intersection point, TP. This is the real part. Okay. And this is the imaginary part. Okay. So TP is pi divided by IMG, which is 0.296 seconds. TP new is 2/3, okay, of TP, so it will become 0.197 s. Okay, the new peak time. Then the omega n also will be 18.58 radian per second. So therefore, the new closed loop pulse will become minus 8.47 plus J 16.54. Yeah. Okay. Then you calculate the angle and the length. Okay. So this will become the test point for the new spec. Okay. Right. So you calculate the theta 1, theta 2, theta 3, theta 4, and theta 5. Okay. Because we have zeros for the PD here. And the existing zeros at minus 8, the existing poles at minus 10, minus 6, and minus 3. So theta 1, theta 2, theta 3 is due to the poles, theta 4 and theta 5 due to the zeros, equal 180 degrees. So you get this zeros is at 19.88 degrees. Okay. So the new zeros will be at minus 54.21 over there. Okay, but after we calculate the theta and the alpha. Okay. Then after you get the minus 54.21, you calculate the length because you want to know the K value. Okay. So from the computer, the K value is if I remember. Okay, so you calculate L1, L2, L3, L4, and L5. L1 and L2 is due to poles. L4 and L5 is due to zeros. Okay, so this is zeros. So this is poles. Multiply, then you get 6. That is the value of the gain at that point. Do we need to draw the original root locus? So in real solution, don't need. But in the assignment, you have to. So the peak time now is 0.297. The desired pulse is here. And the angle of the zero is 18.37. Thus, Z is equal to 55.92. Okay. So that is PD. Finish. Khalas. Now we go to PI controller. Okay, to reduce the steady state error. You just choose these values, which is near to the origin poles, okay, at the origin, and 0.5. Okay, so you can choose 0.5 or you can choose 0.1 or 0.01, no problem. Okay, then you cascade it together. Okay, cascade it together, become here, right? So you cascade it together and then you draw, then you will get KD at 4.6, KP is 259.5, and KI is 128.6. You compare this with the standard PID transfer function. Compare. Okay? PID standard transfer functions. So that's why you get the KP, KD, and KI value. Okay, like this. Okay, so this is the standard. Okay, so this is what you get from the calculations. Okay, and then compare, then you get the value of KD, KP, KD, and KI, KD. This value that you will insert inside the PID controller. Insert the value of KP, KI, and KD into the PID controller as shown in the picture. Okay. So time response before controller, meaning that before we apply PID, so 0.298, the peak time, and settling time 0.7, but our concern is on the peak time. Then after that, the TP new will be 0.198, which is we get 0.196. Okay, much faster compared to the previous one. Okay, so this is the uncompensated. This is a PD. Okay, and this is a PID, which is much better. PID much better than PD when we apply for PD. Okay, so we stop here. Okay, next week we will go for PID tuning. Okay, tuning PID. Okay, so you need to tune this value, 3 values together in order to achieve the spec design. Okay, any question guys? Ada soalan nak tanya?
Sir, about third pole, right? Can I ask about third pole? The third pole is the pole that's closest to the JW axis, right?
Yeah, third pole.
Yes.
Far away. Far away.
Farthest.
Not farther lah. There is a ratio for it, kan? Third pole. Kan? Bagi macam contoh tadi tu kan.
Example 6.
Can you give me dia punya tu?
Dia punya
Second order derivative S square.
oh, it's S plus 8. Oh, it'll be S characteristic. S plus 3, S plus 6, S plus 10.
Apa dia?
S plus 3.
Tak apalah. Let's say 8S plus 2. And what is the root for this? The roots.
4 plus minus square root 14.
Yes. Minus
4 plus minus square root 14.
Plus minus
square root 14.
Square root 14 apa?
Square root 14 is 3.74.
3.74 plus k equal to 0. So this is your third pole. S plus T. Katalah T ni third pole. This is your third pole.
Okay.
So you plot that, kan, alpha omega. So this one will be here. This is dominant pole, dominant, kan?
Yes.
So third pole is here. Okay. Okay.
So, sorry, my question was not third pole, it was dominant pole. Dominant pole is the closest.
No, dominant pole is the closest lah.
Okay.
But that's dominant ni maknanya very high influence towards the output of the system.
Previously in example 6, the answer was not.
Example 6, okay, what's wrong with it? Example 6. Example 6 bukan PID, PD.
PD, yes.
PD. Ni PD. Okay, what's wrong with it?
Let's go to the.
Okay. This one.
Example 5, bawah lagi.
Bawah lagi. Bawah lagi.
Bawah lagi, yes. Lagi.
Okay.
There we are. Atas.
Ni.
Yes. Wait. Where are we?
Second order. Second order mana ada third pole. In this case, tak ada third pole.
Sorry, it's in PID. My mistake. PID.
Lagi ni menjak puasa.
Sorry, doktor. Pening kepala.
Balik. Relax. Okay. Ni kan?
Bawah lagi. DP graph. The graph of it. Yes, there we go.
Graph.
So the dominant pole, with the bawah lagi. With the values we can see clearly. There we go. Yes. So which one is the dominant pole again?
Dominant pole. Dominant pole is the
if I recall the
connection between the damping ratio and the root locus. So where is your damping ratio line? This one.
Yes.
Where is your root locus in damping ratio line? Where is your root locus here? Root locus path kan laluan. Yeah.
So the intersection.
This one. Intersection.
Oh, so it's not -3.
Negative.
Dominant pole. There's a pole in the pole nearest to the JW axis is on the real axis, right? Is that the -3 one?
-3. Mana ada -3? There is no -3.
Tu dekat bawah. Tengah-tengah. In the middle.
Mana? -3 mana? Where is -3?
-3 pole.
I think he's talking about the open loop pole.
Open loop, okay.
What?
Open loop is here. Open loop is this is open loop.
Yeah, there we go. There. Isn't that the dominant pole? No.
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 Open loop is open loop. Because when we talk about root locus, we are talking about closed loop.
I see.
Each point of this is a closed loop. Closed loop. Each point of this is a closed loop with different key value. Loop is from the function just now, which is -8 open loop zeros, -10 open loop poles. This one is -3.
I see.
And -6. So dia punya that is open loop poles. So when they start the path, so it become closed loop poles. Okay, because closed loop poles ni dia punya key is vary. Every point of this different key. Every point of this different key. I can see that students having difficulties to understand the root locus concept because the marks of the quiz one is so and so average about 2.5 out of 5. 50% understanding, not 100%. Only one student managed to get 4.5. No student get 5.2. Over. So you have to read again the book chapter that I give to you. Okay, read the content, the paragraph, word by word, line by line, paragraph by paragraph to understand because my slide is very brief. Okay. Yeah.
For this example, right, the third pole is 8.16, right? It's not more than 5 times, right, compared to the dominant pole. So still,
okay. The third pole is here. I delete. Oops. The question is
it's not more than 5 times, right? So it's the approximation value.
This is by computer, is a real value. Okay. Third pole minus 8.16 kan?
Yeah.
Pole, dominant pole is minus
5.4.
J10.6 kan? What is your question?
Is the so this for this case the approximation as second order system is not valid
Not valid.
because
We have to find the ratio first.
but the
What-
ratio is not more than 5, right?
Wait, minus 8.16.
Divide by
Berapa? How much?
hang on, let me calculate.
8.16 divided by 4.
It's 1.5.
1.5.
Huh?
1.5.
1.5, which is less
than
than
5.
5. Okay, less than 5, meaning that, second order approximation is not valid because less than 5. At this point, So if more than greater than 5, it's okay. 5.1 lah. Even 5.0 also is marginal or critical.
Okay.
Okay, guys, have a nice weekend. Okay, it's a long day for Ramadan. So today breakfasting at 11 p.m. Okay.
Got test coming up, doctor.
Sorry.
We have a test this Saturday.
This Saturday. Oh, another subject, not my subject.
Yeah, power electronics.
Good luck for that. Oh, power electronics. That's a difficult one. All right. Okay. Thank you very much. See you next week.
Doctor,
Bye-bye.
Thank you, doctor.
when is our test one?
Ahmed? Ahi?
When is our test one?
Next one will be after Eid Mubarak. After Raya. After Eid Mubarak.
So there is no specific date for it?
I will inform from time to time. The what do you call that? Quiz will be in May, early of May. Quiz 2.
All right.
Quiz 2 is on chapter 2, PID.
Okay, doctor.
Okay, another 5%. Okay. We'll be updated all the information, important information in the WhatsApp. So please make sure you read your WhatsApp.
All right. Thank you, doctor.
Shukran, Akhi.
Thank you, doctor. Waalaikumsalam warahmatullahi.
Assalamu alaikum.
Waalaikumsalam.
Astaghfirullah.